Okay, good morning. Let me start by reminding us of the last topic we discussed last time. Um, After introducing the concept of state feedback, where instead of simply looking at the output of the system only, we decided that we will feedback the entire state vector of the system. So as many variables are in the state vector of the system, we are going to feed them back and look at them continuously in order to control the system, which means we are going to look at them continuously in order to calculate the input that we put into the system. And as you may recall, the reason we decided to do that was the limitations we faced with the output only feedback. When we only feedback the output, we have to live with a certain set of location of closed loop holes, which is described in the root locus of the system. For example, for the last system, or one of the systems that we repeatedly look at, this blue figure on the slide here is the root locus of the system, which means as we change the controller gain with output feedback only, we could only put the poles somewhere on this root locus. But that somewhere, some location may not deliver the type of performance that we need, may not deliver the type of natural frequency that is expected to deliver a certain response, or the damping ratio that is expected to deliver a certain response. So the solution that we introduced was, instead of only feeding back the output, we are going to feed back the entire state vector. And we talked about the fact that if A of closed loop, when we are feeding back the output only, is A minus B times C times K, A of closed loop, when we are feeding back the entire state vector, is going to be A minus B times K. And we discussed the fact that K in the second design, where when we are feeding back the entire state vector, is going to be a vector itself. So we are now talking about controller gain, a controller gain vector, which has as many elements as the order of the system. So in this case, when we are dealing with a second order system, the controller gain has two elements. So we have two design variables to choose in order to deliver the type of performance that we need to deliver. The next topic that we discussed was around the question of controllability. Is it possible to place the poles of a closed loop system anywhere we want at all times for all systems? The answer, unfortunately, is no. There is only a subset of systems that offer that. And in order for a system to have that property, the system should be controllable. And in order to check whether or not a system is controllable, we construct this reachability matrix that is made of matrices B and A of the system, of the open loop, let me repeat, of the open loop. So N here is the order of the system. So if you're dealing with an nth order system, this has N columns. Each of these is going to be a column for this W reachability. So the dimension of the reachability matrix is the same as dimension or the order of the system. So if you're dealing with a third order system, reachability matrix would be a 3 by 3 square matrix. And based on the fact that the complete response of the system is shown with this integral, effect of homogeneous and effect of input through the convolution integral, we said another way of expressing the same thing of the concept of controllability is a system is controllable if there exists an input, exists an input to get the system from its initial condition over a given time to any desired final state. When we say state, we mean state variable, combination of state variables. So through this integral and the fact that e to power at is through this expansion, series expansion, we decided that if the reachability matrix has an inverse, the system is controllable. And in order for that matrix to have an inverse, we need for its determinant to be non-zero. So the condition, the bottom line condition is that the reachability matrix should be non-zero. Then we looked at an example that we have discussed many times. And in this example, we looked at two different cases. Case one is the usual, when the flow comes to the first tank and then through the first tank flows to the second tank. And the other possibility was, if we remove this input from the first tank, the control input, instead of entering the first tank, if it enters the second tank. So we looked at both of these cases, and through setting up the reachability matrix, we showed that the first case is a controllable system, where we can, when U enters the first tank, when we can put the closed loop poles or eigenvalues anywhere we want on the complex plane, and if we move the input to the second tank, the system becomes not controllable. So we can't put the closed loop eigenvalues anywhere on the complex plane that we want. So we calculated both reachability matrices. One was controllable, and the other one, the second case, was not controllable, as we expect. Now we are going to go to the design step. So if you recall, we did design an output feedback system already for this system. Do you remember that? We did design an output feedback controller for this system. Already have done it. We assumed some numerical values for A1, A2, C1, and C2. Let's make those assumptions again. So we are going to assume again that A1 is the same as A2, and they both are equal to 1. C1, I think we decided for C1 to be 5, and for C2 to be 1. And the unit for A obviously is meter squared, and for this is meter squared per second. So we made that assumption. And if you make that assumption, A1, C1, A2, and C2, you now have numerical values for A and B matrices. And so let's go ahead and write those matrices. So matrix A then would be, what is the first element in matrix A? It's minus C1 over A1, so it becomes minus 5. This is 0. Then this becomes C1 over A1 positive, so this is 5. And then this is minus C2 over A1, so it's minus 1. And for the case that is controllable, the input enters the first tank. So this is 1 over A1, which is 1, and this is 0. Please double check to make sure we are doing this correctly. Okay, so these are A and B of the open loop system with the numerical values that we assumed for A1, A2, C1, and C2. So let's check one more time. So the A matrix is minus C1 over A1 becomes minus 5. C1 over A2 becomes 5. This is minus 1. And this is 1. And this is 0. So this is the case the system we showed was controllable. So we are going to follow that path. The system that is not controllable, obviously we can't design a full state feedback control. If we have time, we can try that to see what goes wrong if you try to design a full state feedback control with that. Okay, so this is A and B. the next step is to form the closed loop A. So A closed loop, so it's A minus B times K. So this is A, which is minus 5, 0, 5, minus 1, minus 1, 0, and K is always a row vector, so it's made of K1 and K2, so it's a vector of controller gains. So this becomes, if you carry out this multiplication, so this has 2 rows, 2 columns, so row 1, column 1 is 1 times K1, so it's K1. Row 1, column 2, the same way is K2. Row 2, column 1, row 2, column 2. So we need to subtract this from matrix A in order to find the closed loop A. So A closed loop therefore is a 2 by 2 matrix. So it's minus 5 minus K1, so minus 5 minus K1, 0 minus K2, so it's minus K2, 5 minus 0, 5, and minus 1 minus 0, it's minus 1. So we found the closed loop A matrix. The next step is in design, is to find the eigenvalues of the closed loop system. And in order to find the eigenvalues of the closed loop system, we'll set up which determinant? Determinant of lambda I minus A closed loop, and we'll set that determinant equal to 0. That's how we find the closed loop eigenvalues. So that determinant of lambda I is lambda 0, 0 lambda. So, and we are going to subtract from it this matrix. So lambda would be subtracted by minus 5 minus K1, so it becomes plus 5 plus K1. 0 minus K2 becomes simply K2. 0 minus 5 becomes minus 5. And lambda minus 1 becomes lambda plus 1. So if you carry this, this becomes lambda squared plus K1 plus 6 lambda plus 5 plus K1 plus 5K plus 5 K2, and that is equal to 0. So we can rewrite this equation one more time. Lambda squared plus K1 plus 6 times lambda plus, so we have K1 plus 5 K2 plus 5 equals 0. So what is this equation? This is the characteristic equation of the closed loop system with a state feedback. So this is with state feedback. So in order to compare what we have accomplished by going from output feedback to state feedback, we need to look at the characteristic equation we got with output feedback. So let's go back in our notes and find that characteristic equation. Did we ever find it? I think we did. On slide 257, our objective was to design an output feedback controller for this system. So we had Y as a feedback signal. We compared it to R, introduced E. So what we did there is we formed our closed loop A through a different formula because it's a different controller. So it was A minus K times B times C because output is being fed back here. So we formed the A closed loop matrix. We found the characteristic equation, and this is the characteristic equation. So we didn't quite carry out the multiplication. So let me go ahead. Or did we do it in another form? Did we do it in no, I think we didn't carry out this multiplication. So this is coming from where we did it with a transfer function. So let's go ahead and carry out this multiplication. So it becomes a1, a2 lambda squared plus a1 c2 plus a2 c1 times lambda plus c1 times c2 plus c1k equals 0. And if you wanted to give it the appearance or closer an appearance of an appearance to the standard second order characteristic equation, we can divide by a1, a2, and this becomes lambda squared plus c1 over a2 plus so plus c2 over a2 plus c1 over a1 times lambda plus c1 c2 over a1 a2 plus c1k over a1 a2 equals 0. So that has a closer appearance to the standard second order. So if someone would read this equation to me, I'm going to write it down under the other characteristic equation we got from state feedback and compare them side by side. So I do remember we had lambda squared. So what is next? It was C1, C2 over A2. So we have C2 over A2 plus C1 over A1 times lambda plus C1, C1, C2 over A1, A2 plus so this was with output feedback. Right? So this was with output feedback. Now, to see what the possibilities are, let's go ahead and bring out a third characteristic equation. That third characteristic equation is the standard form of characteristic equation for a second order system. So it's lambda squared plus 2 zeta omega n times lambda plus omega n squared equals 0. This is the standard second order system. Standard second order system. Where we know exactly where the poles of this standard second order system is located. So we know the real part, for example, is minus zeta omega n, and a pair of complex conjugates are located at plus minus omega n square root of 1 minus zeta squared. So exactly we know how this system behaves based on the fact that we know where exactly the two poles of this standard second order system are located. So we have a lot of information. And the reason we bring this in to see what each of these two control methodologies offer us. So let's start from output feedback. Output feedback. As you change, now remember, A1, A2, C1, and C2 are not design variables. They're fixed. We have two tanks, which essentially gives us all of these numbers. So these are not design variables. The only design variable with output feedback is variable K. So we have a freedom with, of course, limitations to choose K in order to deliver the performance that we want. So what is the effect of K? As you change K, what are you affecting? How can you tell? You need to compare the characteristic equation of the output feedback, for example, with the characteristic equation of the standard second order system. So as you change K, I'm going to repeat my question. As you change K for an output feedback system, what are you affecting in terms of location of the two poles of the closed loop system?
The natural frequency.
Any other ideas? So we have one answer. The answer is we are going to affect natural frequency. And maybe damping ratio. So how could we tell? How could we be sure? Because there are two possibilities here. The way to be sure is simply comparing where K affects. What coefficient in the characteristic equation is going to be affected by changing in K? Is coefficient of power 1 of lambda being affected by changing K? Do you see K at all here? So that means K is not affecting the combination of zeta and omega n. But when you look here, you see K, which means K is going to affect omega n. Do you remember the shape of the root locus of this system? If you do not, it's time to go to MATLAB and recreate that root locus. So go ahead and recreate the root locus of this system. So let's go to, you can go to MATLAB. I'll go to the online version. So how can we create the root locus? We need to introduce the A matrix of the closed loop. So the A matrix of, I'm sorry, the open loop rather. The root locus works based on open loop. So A matrix of the open loop is minus 5, 0, 5, minus 1. So it's minus 5, 0, 5, minus 1. This is the A matrix. The B matrix was simply A semicolon 0. So this is the A matrix. This is the B matrix. So we introduce A and B. So the command is R-locus, and I want to know how root locus can be created with a state space. So you need to give it your system essentially. So we need to define a state space model. So I have already defined B. I'm going to define C. So we chose H2 to be our output. So 0, 1 is our C matrix, and D is 0. So our system is going to be the state space model made of A, B, C, and D. So it says, okay, I know A matrix of your system is -5. After you type SS for state space with A, B, C, and D, it recognizes that you are defining a system. It says, okay, I know A of your system is -5, 0, 5, -1. B of your system is 1, 0, which is the relationship between input and x1 and x2. C is given and D is given. So it says, okay, I understand this is your system. Then what you should be able to do is to type R locus of this system. So you're giving MATLAB the open loop system, and it is going to construct a feedback system with the output feedback only, and draw the root locus. On the other screen, I'm going to bring the actual MATLAB version. So we can click on that. The benefit of the MATLAB version is that you can click on it and see the changes. So the same way, I'm just going to repeat -5, 0, 5, 1. 5 -1 rather. That's A. B is 1, 0. C is 0, 1. And D is 0. So system is state space of A, B, C, and D. And so I typed everything one command after another one simply by putting a semicolon. So if you put a semicolon, you can keep typing your next command. Okay, so let's look at our root locus. So what is happening? This system has two poles. In open loop, the system has two poles. One of them is located at -1. The other one is located at -5. And we already knew that. We already had found these in previous class. So this locus shows you, as you change, if you have MATLAB open, please go ahead and click on it and drag this around. So I'm going to explain through the online version. So as you increase controller gain, the two poles will start moving. So the one that is located at -1 is going to move to the left. The one that is located at -5, for any non-zero value of k, they start going two other poles located elsewhere, not at -1, at -5, closer to this -3. So at some value, which I think determined was 0.8, if I'm not mistaken, at some value for k, the two poles would be identical and they would be both located at -3. Now, as we change the controller gain from 0 to 0.8, are we changing anything at all? What are we changing between natural frequency and damping ratio? While the two poles are real, do we have anything other than 1 for damping ratio? The answer is no. The damping ratio is greater than 1, and as they meet exactly at 3, it's exactly equal to 1. Afterwards, the damping ratio is reduced. So as we move up and down, damping ratio goes down, but throughout this, we always increase the value of natural frequency. So the distance to the origin is getting larger and larger and larger and the damping ratio simply goes down. So we don't have, in other words, we don't have simultaneous control on value of natural frequency and damping ratio. So the change in damping ratio is a byproduct, in a sense, of changing natural frequency. Okay, so let's go back and do the same test, this time for our state feedback. So compare power 1 of lambda, the coefficient of power 1 of lambda, which is k plus 6, with 2 zeta omega n. So that tells us what? That tells, by adjusting k1, we have the potential of adjusting simultaneous zeta and omega n. And here, k1, k2, and 5, by adjusting them, we have the ability to adjust omega n. So the design would be to decide what value we want for omega n and what value we want for zeta, and solve for k1 and k2 to get to those values. So that's the way to solve it. So let's go ahead and solve a design problem. So let's assume that we want so we want, let's say, zeta to be exactly equal to 1, so critically damped system, and we want natural frequency of the system to be 5 radians per second. So I'm going to give you a minute to find K1 and K2. Okay, so if you solve these two equations for these two unknowns, you can see k1 plus 6 is equal to 2 zeta times omega n. If you substitute for omega n and zeta, 2 zeta times omega n becomes 10. And 5, k1 plus 5, k2 plus 5 is equal to omega n squared, just by matching the value of coefficient. Omega n is 5, so this excuse me, is equal to 25. So from here you get k1 of 4, and you bring k1 of 4 into this equation, and you find k2 to be 16 over 5. Okay, we can do the same thing, but with the place command. You remember the place command that we used before? So you can go to MATLAB and use, so you need to first of all decide where the two eigenvalues of the closed loop should be located. So we know for a second order system, the two eigenvalues are located at, let's define zeta first. So zeta, in this case, we want it to be 1. Omega n, we want it to be 5. And we know the two eigenvalues, EIGs, are located at minus zeta times omega n plus j times omega n times square root of 1 minus zeta squared. That's the first of the two eigenvalues. The second one is minus zeta times omega n. This time is minus j times omega n times sqrt of 1 minus zeta squared. So the two poles, let me write the equation down. So the two poles for this standard second order system, as we know, the two poles for the standard second order system, the two poles lambda 1, or eigenvalues rather, are equal to minus zeta omega n plus minus j omega n square root of 1 minus zeta squared. We know that from before. So every time that we have a second order system with known value of zeta and known value of omega n, we know where the two eigenvalues are located. So let's go ahead and look at the eigenvalues. It is always going to be the case whenever, at any time when zeta is 1, we'll have two repeated poles. That's a litmus test. That's a sanity check. So every time that zeta is 1 for a second order system, the two poles, the two eigenvalues are on top of each other. That's the only possibility. So this checks out. So the two eigenvalues are exactly located at -5, which again is expected. The distance is to the origin is 5, which is equal to the natural frequency. Then the command is place. So place, we need to give it A and B and the eigenvalues. I think these are the only three inputs that the command needs. And it basically says, okay, these are the two controller gains. K1, that is multiplied by the first state vector, is 4, and K2, which is multiplied by the second state vector, is 3.2. Does it match with what we found in our hand calculations? Yeah, 4 is 4, and 16 divided by 5. Yes, sir.
That command doesn't work on the actual version of MATLAB.
You're absolutely right. You know what the reason is? Because the two poles are repeated. So MATLAB, so they have fixed that in this online version, but MATLAB has a second command called ACKER. So ACKER. Try that. So ACKER, I think, is the command. So help ACKER. I think that's So it's exactly the same way as place. You just, instead of place, type ACKER. So give it again A, B, and the place of eigenvalues. So if you have, this is Ackermann's formula. It's a different formula and it works for repeated. So what they have done in the unknown version, they combined the two into one command. So it's all place.
That comes out as 14, not 4, but the second one's correct.
So yours, first one is 14. Something is not matching with what we are doing. Either your A matrix or B matrix. So please double check everything. See if your zeta is the same or your omega is the same. The formula is the same. So both of your eigenvalues, are they at -5 and -5?
Yep.
So that's the first check. Then look at
Matrix A is 5, 0, semicolon, 5, -1.
the first one should be -5, 0 in the first row. Yeah. Look at our A matrix here, right here on the screen. It's -5, 5, -1. So that could be it. So what you want to check is look at eigenvalues of matrix A, the open loop, So when you look at eigenvalues of matrix A, where are they located? They're located at -1. So the way to find eigenvalues of a matrix is a built-in function to find eigenvalues and optionally eigenvectors. So for A matrix, when I type A, but when I type EIG of A, I get an error. Subscript indices must be either positive, integer, or less than. Let me try it here. EIG of A. So the two eigenvalues, if you look at the middle screen, for some reason the online version doesn't give me the eigenvalues. But if you look at the eigenvalues of A, they should be -1 and -5. Did it work once you fixed it?
Oh, mine, yeah.
Yeah. So the eigenvalues of A are at -1 and -5. Okay. So you can do the same for any other value of zeta and omega n. So for any other value of zeta and omega n, you can perform the design over again. Okay. So the next thing we are going to do is to actually implement this control in simulation. So we are going to use MATLAB and implement this state feedback control and see as we change the control again, do we really see the behavior that is associated with those poles? So let's go ahead and talk about the block diagram. So let me remind you of the physical system one more time. The physical system has this appearance. So we have an input that enters the first tank, that has its own dynamics, and then the output of that tank enters the second tank, which has its own dynamics, and each of the two levels of these two tanks is one of our state variables. So we need to create a block diagram that reflects this and gives us access to x1 level of the first tank, x2 level of the second tank, so we can implement our full state feedback control. So let's go ahead and create that. So what we need, so you're going to first create the block diagram, and then we are going to implement it in Simulink. So either you can open Simulink and follow along, or you can follow along and then create Simulink at a later time. So what we need is this. So U enters the first tank. So this is tank 1. That's the dynamic. So U enters here. The output of tank 1 is x1, which is the level of the first tank. And this enters the dynamics of the second. And x2 is coming out. So we are going to feed back both x1 and x2, multiply this by negative k2, and multiply this by negative k1, and bring these two together in a summation block. So we are going to add these two together and then bring this up, and then there is a pre-filter that gets multiplied by r, and this comes here with a negative sign, positive sign. This comes with a also positive sign because the negative sign is already implemented in K1 and K2, and this is our controller base. Before we implement it, do you have any questions on the block diagram? Do you see how it works? So in other words, what we are saying is U as the input to the closed loop, to the open loop system rather, is equal to KR times R minus K times X as the state vector. And what is minus K times X? Let's further elaborate. So this is KR times R minus K1 times X1 plus K2 times X2. So K is a vector. K is a row vector, 1 by 2. X is a column vector, 2 by 1. So when you multiply them by each other, they become a scalar. So K is the dimension of K is 1 by 2. The dimension of X is 2 by 1. So when you multiply them, you get a scalar out. So which is K1 times X1 plus K2 times X2. So another way to look at the exact same block diagram is this. So you feedback X, you multiply it by the block minus K, and you add it to R times KR. Ours is more detailed, so we separate K1 and K2. Okay, now we need to know what goes into the first block for tank 1 as the model, and what goes into the second block as the model for the second tank. And we have already solved that. If you look back, um, what we worked on, when we worked on this system for in output feedback, I think we solved that. Didn't we solve this at some stage? If not, we can do it right now, but I thought we solved it. Yeah, here. So the block for the first tank is 1 over S plus 5, and the block for the second tank is 5 over S plus 1. Where do they come from? They come from simply taking the differential equation associated with the first tank and turn it into Laplace, and taking the differential equation associated with the second tank and turn it into Laplace. So that's what we are going to implement here as well. So let me rewrite them here. Okay, so what I just said is this. For the first tank, the model we have is this. We have A1 H1 dot plus C1 H1 is equal to U. That's the model for the first tank. For the second tank, we have A2 H2 dot plus C2 H2 is equal to C1 H1. So that's what we have for the second tank. If you take, so the model for tank 1, if you take that first differential equation into Laplace domain, it becomes A1S plus C1 times H1 of S is going to be equal to U of S. And for the second tank, so for tank 2, that becomes A2S plus C2 times H2 of S is equal to H1 of S. So basically what goes into the first block where it has the label of tank 1 is X1 is output, U is input. So X1, by the way, is H1. So let's clarify that X1, the first state variable is H1, and X2, the second state variable is the level of the second tank, H2. So what goes into the first block is H1 as output over U as input, and that is equal to 1 over A1S plus C1, which in our case is 1 over S plus 5. What goes into the second tank, X1 is its input, X2 is output, so so that's H2 over H1 is the model that goes into the second, is equal to 1. Oh, I'm sorry, I forgot. What did I forget here, guys? If you look at this differential equation, if you take this into Laplace domain, what is missing? So we took this differential equation to Laplace domain. What did I forget to write? C1 that is multiplied by H1. So I'm going to write it right here. So C1 should be multiplied by H1. So therefore, this is actually C1 over A2S plus C2. If we substitute the numerical values, this is 5 over S plus 1. Okay? So when you're ready, open Simulink and implement this exact configuration. And for now, we are not going to worry about KR. We haven't discussed about calculating KR. So for now, assume KR is 1, or simply just connect R to that summation sign. Okay, so let's go ahead and basically create this block diagram in Simulink. Yes, question.
For that U equals equation right there, is that K sub R times R?
Mm-hmm. Yeah, KR that is in that block. Do you see the block on the top?
Yes.
Yeah, that's KR.
Okay.
So yeah, that's KR times R. Minus K1 times X1 minus K2 times X2. So please open Simulink and create this block diagram in Simulink. So I'll give you a couple of minutes to create that block diagram in Simulink.
Are the K2s constants? Which block do you use for K2 and K1?
Oh, these are gains. Yes, yeah. All three Ks, KR, K1, and K2 are gains. Yep.
Professor,
Yes, sir.
how did you turn those gains around?
Control R, or you can click rotate, right-click rotate. So what we are doing here is we are basically creating the block diagram that I have on the slide in Simulink, and so we haven't defined what K1 and K2 are going to be. So the last calculation we did was to place the two eigenvalues such that zeta was 1 and omega n was 5. So that resulted in K of 4 and K2 of 16 over 5. So I'm going to replace K1 with 4 and K2 with 16 over 5. And then we are going to simulate. And then look at the scope. Did we get any errors?
Is there a reason to use like that big circle instead of the two smaller circles?
No, you can do either one. The effect is exactly the same. So what you're doing is, this is x1 times k1, this is x2 times k2, right? So they have negative sign. So instead of creating multiple, I just bring them with one negative sign here, one negative sign here, one plus sign. So the effect is identical. So it's exactly the block diagram that we have on the slide. So you can now see the behavior. So on the same plot, we have value of r, we have value of x1, and we have value of x2. And you can see with this set of controller gains what kind of behavior we have. So if you want, so this is the fastest response possible when you have damping ratio exactly equal 1. I shouldn't say it's the fastest, because if you move the two poles are now located at -5 and -5. If you move them both to -10, for example, you can make the system faster. So you maintain the same damping ratio, but you change the natural frequency to 10. So let's go ahead and use the place command. So let's use the place command for a new set of eigenvalues. So we are going to make omega n instead of 5 rather to 10. So we are creating two new eigenvalues. They should be located at -10 and -10, so they are located. So we are now going to use the command place to calculate the controller gains K1 and K2 that would place the eigenvalues of closed loop at -10, -10. And that is 14 and 16.2. So you can then go to your Simulink and change 4 to 14 and K2 to 16.2 and re-simulate. And you can see the response is faster. And the way you can see it's faster is the time of simulation is the same 10 seconds, but the changes happens much faster, much quicker. Okay, so now what we haven't, so you can change the location of the poles or eigenvalues anywhere on the complex plane and simulate and see the response. For example, we haven't looked at a case where we have oscillation. So let's now go to a case where zeta is not 1. So let's say 0.7. So the two eigenvalues are obviously a pair of complex conjugate, -7 plus minus a j times 7.14. So we have a pair of complex conjugate. We can do the exact calculation for place and find the two controller gains. So it says if K1 is 8 and K2 is 17.4, so you can go back to the simulation on Simulink and make K1 8 and K2 to 17.4. That would put the eigenvalues of the closed loop at these two, -7 plus minus j at 7.14, and you can see the oscillation here. If you further reduce the damping ratio, let's say to 0.3, then you would see more oscillations. So if you changed it to 0.3, the two eigenvalues would be located at -3 plus minus 10, almost 10j, and you can calculate the. So it says you don't. So controller gain 1 can actually be 0, and controller gain 19. So if you set controller gain 1 0 and controller gain 2 at 19, that's how you create those eigenvalues. And for us to see better, I'm going to disconnect R. R is going to stay at 1. So we can, because R is too large compared to x1 and x2, so we don't see as much as we are supposed to see. So I'm going to resimulate this way. And let's get rid of this annoying sound. So you can see the oscillations now much better. So what is happening in the physical system, guys? Let's think physical system. We have one sensor on the first tank measuring continuously the level of the first tank. We have a second sensor on the second tank continuously measuring the level of the second tank. These two data, line of data, come and get multiplied the output of each of these sensors get multiplied by a constant, depending on what we want the system to do. And then this creates effectively the input to the system. So by having a controller gain of 0 and the second one 19, we're essentially creating oscillations in the level of the two tanks. So the level of the tank goes up, comes down, goes up, comes down a few times before it settles at the steady state value. Now, speaking of the steady state value, can we calculate x1 steady state and x2 steady state? Can we calculate, in other words, do we have the right tools to calculate x steady state, the state vector steady state? Can we calculate it? Yes, no. If yes, how? If no, of course, there is no second question. So in order to answer that question, we need to remind ourselves of the state space model. Isn't it ax dot, I'm sorry, isn't x dot equal ax plus b times u, and y is equal to cx plus du? So in steady state, what is equal to 0 in that model? So in steady state, what is equal to 0 in this model? In the state space model? X dot has to be equal to 0, which means a times x steady state plus b times u is 0. So from here, you can find x steady state is equal to a inverse with a negative sign times b times u. So this applies to open loop. Now, if you're interested in finding X steady state when you're controlling the system, instead of A of open loop, you have to use A of closed loop. So if you convert this to A closed loop, you find X steady state when you're doing state feedback. Okay, so we already know what A closed loop is, don't we? We already know A closed loop. We found it. Did we found it? Or yeah, we found it here. Right here. This is A closed loop. Right here. Minus 5, minus K1, minus K2, 5, and minus 1. So let's rewrite it. So we found A of closed loop to be equal to. So what is it equal to? Is it minus 5 minus K1? What is the second element on row 1? Minus K2. What is the second row, column 1? Negative 1. So that's A closed loop, thank you. So let's find inverse of that. So A closed loop inverse is going to be, it's a 2 by 2. So we change place of the diagonal elements and change sign of the off diagonal. So it's minus 1 here. This is K2 minus 5 here, and minus 5 minus K1. And this should be divided by the determinant. The determinant is minus 1 gets multiplied by 5 minus K, so it's 5 minus K plus K1 rather, minus 5K2, so plus 5K2. This is the determinant. So this is the determinant. And this needs to be multiplied by B. So we have B as 1, 0. So let's go ahead and find. So we need to calculate. So X steady state is equal to minus A inverse of closed loops times B times U. So let's go ahead and calculate multiplied by B. B is 1, 0. So the result would be 2y1. So so this gets multiplied by B. So let me write B here. So B is 1 and 0. So this row 1 of A inverse gets multiplied by this column. So what survives is simply minus 1. And from the second one, what survives is simply minus 5. But what is also there is this determinant. So it is divided by 5 plus K1 plus 5K2. And this needs to be multiplied by the input. So let's assume the input is 1. So if the input is 1, and let's go ahead and calculate the last set of gains that we used was, so we wanted to place, if you recall, we wanted to place the two eigenvalues at where zeta was 0.7 and omega n was 10. So for zeta of 0.7 and omega n of 10, was it? Actually, the last one that we solved was zeta of 0.3 and omega n of 10. So zeta of 0.3 and omega n of 10. That resulted in K1 being 0 and K2 was 19. So that tells you,
Professor,
yes, sir.
shouldn't the negative 1 and negative 5,
Mm-hmm.
when you have x steady state, should they be positive 1 and positive 5? Is that minus sign in front of the ACL?
Absolutely, yeah. Thank you. This should be positive, yeah. This is there, so it should be positive, yeah. Or I can put the negative sign for now here, so we know there is negative sign. But that's absolutely correct. Okay, so let's go ahead and calculate x steady state as a vector. So we now know it's positive 1 and positive 5 divided by, what is this number? It is 5 plus 0 plus 5 times 19. So what is 5 times 19? It's 95. So it's 100 basically. So 100. And this times u, so I'm going to put u here. So that tells you that x1 steady state is equal to 100, and x2 steady state is equal to 500. And look at your simulation one more time, please. Look at your simulation. Do you see that? Do you see 0.01 and 0.05 as the steady state values for x1 and x2? Right there on the plot. Yellow and the blue. But is the controller doing what it's supposed to do? So let me repeat my question one more time. Based on what you see in the simulation, is the controller doing what it's supposed to do? If you're nodding in yes, you're correct. And if you're shaking your head in no, you're also correct. Meaning that the controller is doing part of what it's supposed to do, but not entirely. So remember, we said the controller has two essential jobs. One is to shape the transient portion of the response, and our controller is doing a fine job in doing that. So it puts the eigenvalues of the closed loop system where we want them to be located, and it delivers the transient response associated with that. Where it lacks is where? Where it lacks is the second function that the controller should do, and that is to make sure the output of the system matches R. Now in our simulation, what are we saying? We look at our simulation block diagram. We are saying we want x2. So according to the block diagram, x2 should match R. And in our simulation, with any set of controller gains that we have tried, we have placed the eigenvalues at least in 3 different locations, and we kept repeating the simulation. The shape of the transient response changes, but the steady state response of x2, which is the output of the system, which we want to match R, doesn't happen. So look at it. We calculated value of x2 steady state. x2 steady state is actually 5 divided by 5 plus k1 plus 5 times k2. Right? It is not equal to 1. So the general form, because y is x2, so y steady state, which is the same as x2 steady state, according to this is equal to, according to our calculation, is equal to 5 divided by 5 plus k1 plus 5 times k2. So it's not equal to R, which we chose it to be 1. So we have a problem. So our controller is doing better than output feedback only, but it's not able to deliver zero steady state error. So it's not able to make y equal to r, the output equal to reference input, in steady state. So what should we do? And that is exactly why we have this guy. Which one? This guy. The third controller gain in our case, which we called a pre-filter. So a pre-filter. So now here's the question. What should the pre-filter be so we have zero steady state error? So what should the pre-filter be so we have zero steady state error? So we deliver, the controller deliver what it's supposed to deliver. You're absolutely right. So let's go ahead and change it to 20. But I think you're right. Let's try it. And resimulate. And voila. Your x2, y matches 1. So how did you calculate 20?
They took their steady state.
0.05. So it needed to be 20 times larger. So you said, so, but how did you make x2 steady state 20 times larger?
I mean, you're making the input 20 times larger?
So you are fooling the system, actually. So what you're doing is you're saying, I pretend. See, when KR is 20, look here. When KR 20, what are we doing? We are saying, I know I want y to get to 1. But I see that y doesn't get to 1. It gets to 0.05, which is 20 times smaller than what I want it to be. So I'm going to fool the system and say, I pretend that my r is 20, and it's a linear system, so it will scale up. So it gets to 1/20th of 20, which is 1, which is exactly what I want it to be. Did you see the logic here? So we see that with KR of 1, our steady state response output gets to 1/20th of where it's supposed to be, 0.05. So if we scale up the actual R value, so we are going to make the system to go to 1/20th of that value, which is exactly what in the first place we wanted the system to do. So change that 20 in your simulation and simulate it. But this time KR was 20. What is the general methodology of calculating KR? That's a question that we still have. Of course, we can do the same thing every time. So simulate the system and see where it settles, and then ramp up KR to get to where we want it to be. So let's try another set of control again. So you remember, excuse me, for putting the two eigenvalues at zeta of 0.7 and omega n of 10, we had two controller gains of 8 and 17.4. So go here and change this to 8 and 17.4 and simulate. It seems like we also get, we are okay with 20. Let me resimulate to see what exactly the steady state value is. So with KR of 1, the steady state value is still 0.05. So so that's why 20 still works. So let's look at our equation again. See if it makes sense. So K1 was 8. So y steady state is 5 divided by 5 plus 8 plus 5 times 17.4. So it's 0.05. So it just so happened that these two numbers, we get still 0.05. So that's why even though the two controller gains are different, the value of y steady state is still 0.05. So that's why still 20 would work. But still, we want to solve this problem in a general sense. So let's go ahead and try to figure out a way to find Kr that solve this problem in general. So that's going to be our mission. And for those who are watching the lecture online, we did several simulations, and essentially what we have shown is various type of responses that I have on this slide. So these simulations have been done with various values of zeta and omega n. So the top is for zeta 0.7, omega n of 3 different values of omega n. Omega n of 0.01 radians per second, 0.1 and 1 radians per second. So the two plots are plots of H1 and H2. So you can see if zeta is 0.7, you have simulations. As omega n increases, the speed of response increases. So from left to right, the system becomes faster with the same value of zeta. If you go to another value of zeta and repeat, of course, you have a different set of response. So for each of these cases, we have calculated a different set of k's and resimulated the system. So the question then is, what is the general value that Kr should assume so we have zero steady state error? So y in steady state matches r. And it turns out that value is what we have in the middle of this slide. It's right here. So this is the value of the pre-filter to guarantee that we will have zero steady state error. So what is it? It's equal to -1 over matrix C of open loop times A of open loop minus B of open loop times K, which is what we have found as the controller gain vector for state feedback control, inverse times B. So we need A, B, and C, the 3 matrices of the open loop system, and we need the controller gain vector K. So we need to put all of them together in order to calculate the pre-filter. That would give us zero steady state error. But why this number? Where does this come from? It comes from this fact. So let me get myself a little bit of space. So it comes from, I added it at the wrong place. Okay, so it comes from this fact that so let's go back to our basic state space model. We know x dot is equal to A times x plus B times u, and y is C times x plus D times u. This is the basic state space model. Now, according to this block diagram that we just put together, according to this block diagram, look at the value of input to open loop. The value of input to open loop is R times KR minus K times X. And I have the equation right here. So let's go ahead and write that down next to our state space model. So what did we say? We said in state feedback, so if we are doing state feedback plus pre-filter if that is the case, the input to the open loop is KR, the pre-filter, times R, the reference input, minus K times X, where both K and X are vectors. K is a row vector and x is a column vector. So when they add up, if they become a scalar, so we can add it to the next scalar. Do you agree so far? You're okay? All right. So we are going to go ahead and put this into our state space model. So therefore, x dot becomes ax plus b times k r times r minus k times x. Okay, so this becomes a minus b times k times x plus b times kr times r. Okay, is that okay so far still? So that's the dynamics of the system with the closed loop feedback control plus the pre-filter. That's the dynamics. Now let's think in steady state what we want. What do we want in a steady state? We want in steady state for y steady state, which is equal to c times x steady state, and d in majority of cases is 0, so I'm not going to write it. So c times x steady state, we want this to be equal to what? What do we want y steady state to be equal to? Look at the block diagram. What do we want? By the way, this is y. Y is the output of the system. x2. In this case, we decided y is x2. So what do we want y in steady state to be equal to? We want it to be equal to r. That's the whole meaning of r. R is called reference input, which is what we want the output of the system to be equal to in steady state. As the sooner the better, of course. So we want this, the ideal case is we want this to be equal to r. This is our ideal. This is the ideal control. So we want c times x steady state to be equal to r. But what is x steady state? We can calculate it from this equation. By setting x dot equal to 0, we can calculate x steady state. So if you set x dot equal to 0, you can calculate x steady state. X steady state would be what? X in steady state would be, this coefficient will be inverse. So it would be minus a minus b times k inverse times b times kr times r. Can you see that from the top equation? By setting x dot equal to 0, x steady state can be calculated. And further, what we know is that c times this x steady state has to be equal to r. So what we know is c times x steady state, which is this. So I'm going to rewrite it. Minus c times a minus b times k inverse times b times kr times r. We want it to be equal to r. From the line above that we said we want y steady state to be equal to r. So that means now that C times A minus B K inverse times B times KR times R has to be equal to R. Which tells you what? If you look at that equation, what is the immediate conclusion? The immediate conclusion is that this has to be equal to what? Has to be equal to 1. If it is equal to 1, then R is equal to R. So which then, the unknown that we are after, what are we doing? Why are we doing this calculation? What are we after? We're trying to calculate what? Do we know what C is? Yes. Do we know what A is? Yes. B is? Yes. K? Yes. So we have designed our controller. We have found K already to put the eigenvalues of the closed loop system where we want them to be. So we know what K is. So we know B. What we don't know is KR. We don't know what pre-filter value should be to give us zero steady state error. So KR, therefore, is going to be equal to -1 over C times A minus B K inverse times B. Okay? So we know the answer to our question for the two-tank system. We know ahead of time that KR is supposed to be 20. Let's see if we can get to that number. Let's see if we can get to that number. So the example that we solved was what? We solved an example where K1 was 0, K2 was 19, so K1 0, K2 19, so let's rewrite them. So K is essentially 0 and 19. So what else? C of open loop is 0 and 1. We are saying H2 is the output. B of open loop is 1 and 0. We are saying the input enters the first tank. And A of open loop was what? What was A of open loop? What is -5, 0, 5, -1? That's what I remember. Please check. So I think it was -5, 0, 5, -1. Please double check. Is this A of open loop? Yeah, -5, 0, 0, 5, -1. So that's A of open loop. So you have everything to do the calculation. So I'm going to give you a minute. Do this calculation, please. So find A minus BK, find its inverse, pre-multiply it by C, post-multiply it by B. That would be a number. Then take -1 and divide it by that number. See if you get KR to be 20. I'll give you a minute. Okay, so I did the calculation on the board. So we know what K is. So the vector for K, we know all four matrices, D is 0, C, B, and A are given. These are open loop. So as the first step, I went ahead and calculated B times K. This became this 2 by 2 matrix. Then A minus BK. Please let me know at any step if your numbers don't match mine, so we can look into it. So A minus BK is this matrix. Then I found inverse of A minus BK, which is still a 2 by 2 matrix. And this 100 is the determinant, so we are dividing by the determinant. Then we pre-multiply that 2 by 2 matrix by C, which is a 1 by 2 matrix, so the result is 1 by 2. And then post-multiplied it by B, so 1 by 2 multiplied by 2 by 1 is a 1 by 1 matrix, otherwise known as a scalar. So this is the result of that multiplication. According to the formula for KR, we have to take minus 1 and divide it by this number, which is what we did at the last step. Minus 1 divided by minus 5 divided by 100. And that gives you KR, which we already knew gives you the perfect answer, the perfect steady state response. Okay, so this is your next exercise. There is a mass spring damper system with force as input and displacement as output. Is this system controllable? What if the output is velocity? Would that system be controllable? So you need to go ahead and calculate matrix A, matrix B for that system, and then set up the reachability matrix. So I'm going to give you a minute to solve this problem, and then we'll work on it together. So this is the system. Its differential equation we already know by setting up the free body diagram is going to be mx double dot plus bx dot plus kx is equal to force. The two state variables are force and their displacement and velocity. The input is force. We are considering two different cases. One is the output position, so y1 is equal to x, and the second case is where output is equal to velocity, so y2 is x dot. So x double dot is equal to 1 over m f minus bx dot minus kx. So f is u, x dot is the second state variable, I'm calling it x2, and x is the first state variable, I'm calling it x1. So rewriting this into a matrix form, A is going to have 0, 1 in the first line, and minus k over m minus b over m. B has 0 also on the first line and 1 over m on the second line. We have two possibilities for C matrices. When output is position 1, 0, when output is velocity 0, 1. So these are the two C matrices. Any questions before we move forward? So the question is this system controllable, and whether or not the choice of output would have any bearing. So how do we check controllability? We create this matrix that is made of B as the first column and A times B as the second column. This is a second order system, so we'll stop at power 1 of A, which is n minus 1, 2 minus 1. And if this matrix has a non-zero determinant, so if W reachability is non-zero, then that means is controllable. So in a sense, we have already answered the second question. The second question was, what if the output is velocity? The answer is, even though we haven't established if the system is controllable or not, we know under which condition the system would be controllable. But let's go ahead and answer the second question first. The second question is, what if the output is velocity? What is your answer? Doesn't matter, because C doesn't appear in the controllability matrix. So it doesn't matter what the output is. It just matters what A and B are, which has nothing to do with the output. So let's go ahead and calculate so A times B is going to be a column vector. So A is 2 by 2, B is 2 by 1, so the result is 2 by 1. So 0, 1, this first row gets multiplied by the column, so the first row is going to be 1 over m. The second row is going to be multiplied by the column 2, so it's minus b over m squared. So minus b over m squared. So that's A times V. Now we can go ahead and assemble the reachability matrix. So that's B, 0, 1 over m. And then the next one is AB, so 1 over m here, minus b over m squared here. So that's the matrix. Now we can calculate its determinant, which is going to be minus 1 over m squared, which is definitely non-zero. So if we have a limited mass, if the mass is not infinite, this system remains controllable. Which means what? What does it mean for this system to be controllable? You can choose any eigenvalues you want. So even though the open loop system could be underdamped, for example, So the value of K and B could be such that the open loop system is underdamped, which means what? Which means if you apply a force to it, it will oscillate and then settle somewhere. You can make the closed loop system whatever you want, including making it critically damped. So by properly changing the force, you can position the mass in a way that the system does not oscillate. Let me repeat. By properly controlling the force, which is the input to the open loop system, you can displace the mass from one position to another one without any oscillations if you desire for that to be that way. Okay? Are you are you ready to design a controller then? Excuse me. So let's go ahead and at least start. I know we don't have much time. Let's go ahead and at least start designing our control system. So let's say so for the closed loop system, so for closed loop, what we want is an omega n of, let's say, 1 radians per second. But we want zeta to be exactly equal to 1, which means we want for closed loop eigenvalues to be located where? Can you tell me? Where are the two eigenvalues? They're both exactly at -1. So -1 and -1. That's the meaning of zeta being 1 and omega n being 1. So they're repeated at -1. So please go ahead and get started on calculating the controller gains that would put your closed loop eigenvalues both at -1. For that, you need to, as we know, create A minus BK. This is A of closed loop. And let's make some assumptions also to make the calculations easier. So let's make MB1 let's make K also 1. And let's make let's make B 1.4. That's equivalent for the system to be, the open loop system to be underdamped with natural frequency of 1 and zeta of 0.7. That is that equivalency. Okay, so I'm going to stop here and we'll continue next time. Thank you.
Will you be posting a sample final like you did for the last midterm?
Yeah.
And then will the final be cumulative or will it just be over this part?
It would be, we can't make it just on this part. See, whatever problem we solve
Mm-hmm.
has the component of
Yeah,
modeling.
yeah.
So the first portion was modeling, so
Yeah.
even though the focus naturally would be on control,
Okay.
but
It'll still have a little bit of
yeah,
both.
we have to
Okay.
the models. Yeah.